So it says, at a used book sale, 100 books are adult books and 160 are children's books. 70 of the adult books are nonfiction, while 60 of the children's books are nonfiction. Is that right? Okay, if a book is randomly selected, or selected at random, find the probability that it is, okay, we've got some things down here that we'd like to take a look at in just a second. But before we do that, it's going to help us if we can come up with our own contingency table. We talked about a contingency table being a tool that allows us to separate data into two different categories. And so in this case, the categories would be what? Fiction, nonfiction, and adult and children. So they didn't give us the table, but hopefully we have enough information so that we can come up with our table. Okay, so I'm going to do adult and children, and then fiction and nonfiction. Okay, so we've got 100 books, it says, are adult books. So at the end of the day, the total for adults is 100. All right, and 160 are children's books. Okay, so that's how we can place those numbers. But then they tell us 70 of the adult books are nonfiction, which means what? 30 have to be fiction. Okay, and then we've got 60 of the children's books are nonfiction. So we've got what? 100 that are fiction. And so now we can even add up the total number of fiction books and also the total number of nonfiction, which actually ends up being the same number. Okay, but now that we have that, we can talk about these probabilities. Okay, so the probability of having a fiction book. Going back to our basic rule for probability, we're going to look at the number of books that are fiction and divide that by what? The total. Okay, so probability of fiction. Okay, the number of fiction books that we have altogether is fiction books. 130 fiction books, and then altogether we have how many? 260. So it looks like exactly half. The probability of randomly selecting a book that's fiction is half. Okay, not a children's non-fiction book. Which principle that we talked about last week does this use? Which one? You got to know the principles because that's what the test is about. So something we talked about just briefly. Starts with complement. Very good. The complement. So there's several ways we could get to the answer, but we want to keep the complement in mind. So if we're talking about the probability of not children's nonfiction, that's going to be equal to 1 minus the probability of what? Children's nonfiction. Okay, that's the complement. Okay, the complement of children's nonfiction is not children's nonfiction. So we end up doing 1 minus the probability of children's nonfiction would be what? Over 260. Okay, our total right now is 260. Okay, we'll talk about some cases where we restrict that total a little bit later, but for now we're looking at all of the books. And so 1 minus 60 over 260 gives us 200 over 260. That reduces to something. What is that but in decimal? 0.77. Okay, 0.77. Question? It doesn't matter to me. It's all the same, but you'll need to be able to recognize your answer on the test, because the test will have choices. It really doesn't matter as long as you can match up your answer. I said 260 over 260. That's the same thing as 1. But remember, your calculator will handle it too. So just put it in the calculator, and we really want the decimal when it's all said and done in most cases, because that makes more sense. I mean, we can see 200 over 260, but until we write this as a decimal, it's kind of really hard to really interpret that. This is about 3/4 or 75%. Okay? All right. Okay, an adult book or a children's non-fiction book. Which principle are we applying here? Same thing? Well, maybe. Okay, that might not have been my first inclination, but possibly that works. Or what else could we do? Well, he was saying complement. Something else. If you had not just done this complement, what might you be thinking about? Hopefully. Which one? Addition rule, right? The key word here is or. And so if we're talking about the probability of adult or children's nonfiction, okay, then remember we talked about keyword or. We said that means addition. This is the probability of adult, okay, plus what? Probability of children's nonfiction, and in general we would say minus the probability of both. In this case, can it be both? Can a single book be both an adult book and a children's nonfiction book? No. Okay, so we don't even have to worry about the both. What do we call it when it can't be both? What's the term for that? Mutually exclusive. Very good. Okay, so the probability of an adult book, I think, is 100 over 260, plus the probability of children's nonfiction, is that 60 over 260? Okay. And so we get 160 over 260, or what? 0.62. Okay, very good. So that was a really nice brief summary of what we talked about last week. And hopefully you're starting to think that way. All right, these rules are pretty simple, don't you think? I hope you think so. But no matter how complex the problem, this is where I would start with these basic rules. They work for a long ways, but you got to know them. Okay, moving on. Okay, we got the multiplication rule. We're going to talk about it in 2 sections. The basic rule we'll start with here, and then hopefully we'll get through most of section 5 today as well. But when we talk about the multiplication rule, the key word that we're going to see is and. Keyword and. So we've got events that are happening together. Okay, keyword and. When we see the probability of A and B, the first thing we're going to think about is the multiplication rule. We've got some notation that we need to think about, and this is it in particular. Okay, this is the probability of B given A. And I need you to understand that that means event A occurs in a first trial. I'm sorry, I'm jumping the gun. Okay, A and B. All right. So that means event A occurs in a first trial and event B occurs in a second trial. All right, so A and B. All right, and then represents the probability of event B. Yes, okay, here we are. probability of B given A is what we call conditional probability. Okay, it is the probability of B under the assumption that A has already occurred. And that's going to be super important for us. Okay, probability of B given A represents the probability of B occurring after it is assumed that A has already taken place. Okay, a quick example of that might be, what's the probability of getting a queen given that a red card is drawn? Okay, so, if you think about a deck of cards and we're given that a red card has already been drawn, then it reduces the number of queens, right? Okay, so it's a probability that's based on an event that has already occurred. It's conditional. Okay, so we've got two rules, just like before. With the addition rule, we talked about whether or not the events were mutually exclusive. With the multiplication rule, we're going to talk about whether or not events are dependent or independent. Okay, if our events are independent, then we say the occurrence of A does not affect the probability of B. Okay, all right. In short, we say that the events are, they're independent. If A happening doesn't change the probability of B happening afterwards, then those events are independent. Okay, and that would mean if A and B are independent, then the probability of B given A is just going to be equal to what? If B is not affected by A. Just probability of B. Okay, it's not affected. Very good. All right. If we know that the events are independent, then there is really no conditional probability. B is not affected by A. Okay, so probability of B given A is just equal to the probability of B. If they're not independent, then we say they're dependent. Okay. Okay, and I've kind of run out of space to write my rules in, but the rule for the multiplication event is for independent events, the probability of A and B is equal to the probability of A times the probability of B given A. All right, that's our multiplication rule for, dependent events. Please forgive me. Move this over. Oops. Okay, for dependent events. If the event's independent, then we say the probability of A and B is going to be equal to what? Well, in part, if we just substitute for what we have over here, it would still be the probability of A, but because they're independent, instead of writing B given A, it's just what? Probability of B. Okay? So that's our rule for independent events. I would say that this rule is the more general rule because we can always stop and say B is not affected by A and just write whatever the probability of B was. Okay, this one we only use if we know that A and B are independent. Okay? All right, so here are a couple of things that you should be aware of that affect dependence and independence. And that is sampling with or without replacement. Okay, consider, the urn that always comes up in statistics and probability. Suppose that I'm taking marbles out of this urn Let's say I'm interested in, it's got all kinds of colors. If I'm interested in taking out a blue marble, and then I put that blue marble back, and then I want to take out a second marble. So basically, I've replaced my marble. Then, in that case, when I put it back in, my sample space has not changed, and so the selection of the second marble isn't dependent on the first. Does that make sense? Okay. But if I take that marble out and I don't put it back, I toss it away, then if nothing else, the total number of items in the urn changes, that bottom number. And so in that case, it's dependent. So if we're sampling with replacement, that means our selections are independent. If it's without replacement, the selections are dependent. And if it doesn't tell us clearly, we assume that sampling is without replacement. Okay? So assume it's without replacement unless it states otherwise. All right, so let's see if we can put this together in some examples. Okay, determine whether A and B are independent or dependent events, and then they want us to go on and find the probability of A and B. Okay, so looking at the first example, when a baby is born, it is a girl. That's event A. And then now we have a second baby being born. It is also a girl. Are those events dependent or independent? Independent, okay? The outcome of the second child, the probability of it being a girl is not affected by the fact that the first child was a girl. Okay, so in this case, we would be interested in probability of girl and girl. Okay, right? I see that. I've got keyword and, which tells me to multiply. I'm going to ask myself, are the events dependent or independent? And you would say what? Independent. So this is just going to be the probability of a girl times the probability of girl. Okay? And the probability of a girl is roughly 1/2 times 1/2, and we get 1/4. Okay, questions about that? All right, in this next example, it says when an M&M is randomly selected from 100 M&Ms, it is one of the 8 yellow M&Ms. So that's event A. Event B is when a second different M&M is randomly selected from those listed in dataset 20. It is also a yellow M&M. Would we say dependent or independent? Okay. Dependent. I mean, if we know that when we select it's going to be different, then we must have tossed that first one out. Yes. We assume that it's without replacement. That's right. Okay. All right. So we decided that these are dependent because we've taken the M&M out, and also in this one, I think he tried to indicate that by saying, since it was a different M&M, the only way we can guarantee that is not to put that first one back in there. All right, because there's always a chance if you put the first one back in there that you'll pull it out again. So we had to toss it or eat it or something. Okay, so we got the probability of yellow and yellow. Keyword and. Try, it's going to be so important to write these problems using the keywords that we're talking about and then go from there. So we've got probability of yellow and yellow. And so I'm going to write this because we've already decided that these are dependent events. So the probability that the first is yellow times the probability that the second is yellow, given that the first was yellow. All right, you didn't have to write it top bottom like that. I was just running out of space. So what's the probability that the first one is yellow? Not 1 out of 8, but 8 out of 100. Altogether, we have 8 yellow M&Ms, and there's 100 altogether. Okay, we took that one, we ate it. Now we're ready to select a second yellow one. What's the probability of the second one being yellow, given that the first was yellow? What is it? 7 out of 99. 7 out of 99. That's what conditional probability does for us. Okay? The probability of the second one being yellow depended on the fact that the first one we'd already removed a yellow M&M. Okay, so you can multiply right across the top and right across the bottom. So do 8 times 7, divide that by 100 times 99 in parentheses. I got 0.0056, or would say 7.0057. Okay. All right. So basically, the probability of selecting 2 yellow M&Ms, both of them being yellow, would be 0.0057. Okay. Questions about this? Great. All right. Let's look at some more problems. This next one, it says a random number generator produces a sequence of digits where each can be any of the 10 integers from 0 through 9 with equal probability. Each digit is generated independently of the others. Find the probability that a sequence of 5 digits will consist of all ones. Okay, so remember, we're looking for keywords. I also told you that, don't get confused and don't jump the gun too much when you get ready to look at these problems. Kind of read through it and then make sure you focus on what the question is asking you to find. All right? And that's true in any word problem. If you can't say what it's asking you to find, then you're probably not going to find it. Okay? So find the probability that a sequence of 5 digits will consist of all ones. Now, in that sentence, I don't see and or any keywords. But can we restate this in such a way that we would use our keywords? Okay, how many digits are we selecting? 5, and we want them to be what? Ones. So that means when I select the first one, it's going to be a 1, and the second, and the third, and the fourth, and the fifth. Right? So I just use keyword and. So we're looking at probability of 1 and 1 and 1 and 1. 1, 2, 3, 4, and 1. Okay, you don't have to write it that way, but you got to think that way. All right? So we've got that, keyword and. Now the question that we ask is, are these events dependent or independent? They're what? Independent, okay, because it tells us that they're generated independently of one another. Okay, so then in that case, this is just going to be the probability of 1 times 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 the probability of 1. Or we could have saved ourselves a little ink and time by just writing what? What is it? Very good. Probability of 1 to the 5th. Okay, that's just a little algebra. All right, probability of 1 raised to the 5th power. And so now, what is the probability of generating a 1? 1 out of 10, okay? There's only one outcome that's a 1. There are 10 altogether. And so we get 1/10 raised to the 5th, which is going to be something like, I believe, 0.00001. Is that right? Okay. Questions about that? Or do I need another 0? I think I'm good. Okay, good. All right, questions? Do you see how I'm thinking? Y'all are not nodding. Okay, I need y'all to see how I'm thinking, okay? You have to think this way. You must do it. Okay. All right, here's another problem. Find the probability of drawing 2 cards from a shuffled deck of cards such that the first is an ace and the second is a king. The cards are drawn without replacement. Even if they didn't tell us that, we would have assumed that it was without replacement. Okay, so focusing on what the problem wants me to find, I want to find the probability of what? Ace and king. Okay, and so I see keyword what? And I'm going to think multiplication. I'm going to ask myself, are these events what? Independent. Are they? No, they're not independent because we are not replacing that first card. All right, so the probability of getting a king depends on what I get when I draw that first card. Okay, so we write this as the probability of an ace times the probability of king given ace. Okay, and so the probability of an ace is what? Four out of 52. Okay, there are 4 aces, 52 cards altogether. Okay, I think I said this maybe in the other class, but knowledge of a deck of cards is fair game for the test. So, and dice. All right, just what's all right? Times the probability of a king given an ace. That's going to be what? 4 out of 51. Okay, because we've taken one card out, it's gone. But that card was not an ace, or it was an ace. It wasn't a king. Okay. So we still have 4 kings left. And so we get whatever 16 divided by the product of 52 and 51 gives us what? 0.006. Okay. All right. We'll leave it at that for now. Questions about that? See? It's like riding a bicycle once you figure out what's going on. I hope. Okay, I think we've seen this table before. We'll look at it again. If you're familiar with these results for the drug screening, so it says if 3 of the 1,000 test subjects are randomly selected, find the probability that they all had false negative results. Okay, and then is it unlikely to randomly select 3 subjects and get 3 results that are all false negative results? Okay, and then he says, assume that the selections are made with replacement. So we're interested in the probability of what? Okay, how many? Well, how many are we selecting? 3 false negatives. Very good. All right, do we have a keyword here that we can use? And false negative and false negative and false negative. Okay, so we know we're going to use the multiplication rule. Are these events dependent or independent? Independent because we are doing what? Replacing them. Okay, so in that case, the probability of a false negative is what? 6 out of 1,000. Very good. And these are independent, so we're just going to do what with that? Raise it to the 3rd power. Because altogether we had 6 false negatives. Okay, you see that here? Okay. All right, so 6 over 1,000 raised to the 3rd power is I got points. I got lots of zeros. Okay, I've got, hopefully I did this right. 0.00, 1, 2, 3, 4, 5, 6 zeros. Is that what you all got? Okay, good. All right, questions about that? Okay. All right, well, what if the selections are made without replacement? Then we're still looking at the probability of 3 false negatives. Okay, we can still restate that using keyword and, so the multiplication rules applies, but now they're going to be what? Dependent, right? They're going to be dependent because we're not replacing. So technically, we would say 6 over 1,000 times 5 over 999 times 4 over 998. Okay? All right, somebody give us that number. What? 1? Okay, some more stuff behind it, or that's it? 1, 2. Okay, very good. All right, so I want to make a point about this that is emphasized a little bit later. First of all, did it make a big difference? No. Okay, and the reason why is because only selecting 6 people out of 1,000, or no, we were selecting 3 out of 1,000, right? Which is a very small portion of the population. If every time we select, we're mixing folks up, we're randomly selecting, then it's not likely that we're going to select the same items more than once. Is that right? Yes, no, maybe? Okay. So flip over a little bit in the handout and we'll go ahead and mention this. Right here. Where it says treating dependent events as independent. Okay, if we're not putting the people back, then technically they are dependent events. However, the difference between the calculation for dependent and independent for us, it didn't make that much of a difference, did it? Okay, so we're going to treat them as if they are independent. If I had to do this problem and they didn't have it broken up into those 2 pieces, I would have treated those events as if they were independent, because it wouldn't make that much of a difference. The author even goes and gives really that calculations with sampling are very cumbersome. For us to have to subtract the 1 top and bottom, that could be cumbersome, especially if we were trying to select 12 items. That'd be a lot for us to write out, right? Y'all following me? Okay, so that's what he means by cumbersome there. And the sample size is no more than 5%. If we selected 3 people or 6 people or 12 people, that's less than 5% of the 1,000 that were available. Okay, treat the selections as being independent even if they are actually dependent. Okay, so whether or not they replace it, you know, we're going to treat those things when we have a large population like that and we're only pulling a little bit out at a time. We're going to treat them as if they are independent. Okay? All right. Very good. Let's see. Where were we? All right. Here's another problem. Very typical of what we might see on the test. Acceptance sampling. With one method of procedure, or one method of a procedure called acceptance sampling. I have no idea what that means. Let's see. Sample size is randomly selected. We have items that are randomly selected without replacement, and the entire batch is accepted if every item in the sample is okay. I think that's what that's supposed to say. Among 810 airport baggage scales, 102 are defective. If 4 of the scales are randomly selected and tested, what is the probability that the entire batch will be accepted? Is this scheme likely to detect the large number of defects? Okay, so acceptance sampling is a common procedure. We just got a shipment of 810 scales. Do we want to have to go through and test each and every one of them to make sure that they're working correctly? No. Instead, what we do is we decide we're going to test so many. 4, I think, in this case. And if all of them in that 4 are okay, then we say the batch must be okay. If we find some defectives, then we might say, we either need to look further or we're sending this back. All right? Does that make sense? So that's kind of what's going on here. And we'll see some other examples of acceptance sampling a little bit later. All right? But focusing on the question, if 4 of the scales are randomly selected and tested, what is the probability that the batch will be accepted? So we're interested in the probability that the batch is accepted. Okay? Well, what's to happen in order for the batch to be accepted? For what? It says the entire batch is accepted if every item in the sample is okay. So we get 4 that are what? 4 that are okay. All right? 4 that's one that's good, another one that's good, and good, and good. All right, everybody following me? Okay, I kind of jump to the next part. How do we state this with our keyword? Then we say probability of good and good and good and good. Okay, so we see multiplication rule, and now we're asking, are these events dependent or independent? This is a tough one. Technically, they are dependent, okay? And since they've given us the numbers the way that they have, I'm just going to go ahead and do it as if it's dependent, because that's what it is, okay? So let's just go that route. So we're looking at technically the probability that the first one is good times the probability that the second is good, given that the first is good, okay, times the probability that the third is good, given that the first and second were good, times the probability that the fourth is good, given that the first, second, and third are good. You don't have to write it out, but you've got to think that way. Okay? So the probability that the first one is good is what? What is it? How many? 102. Right? Oh, I'm sorry. Not good. How many are good? 108. Very good. 708 are good, divided by 810. Okay, and then if we're treating these things as if they're dependent, which they are, then we would do 707 over 809, and then 706 over 808, and 705 over 807. Okay. So see what your calculator gives you for that one. What'd you get? Okay, 0.583. Very good. Okay. And so, how do we answer the question, is this scheme likely to detect the large number of defects? Yes or no? No. And what we just said was 58% of the time, this thing is going to be accepted. All right. And considering there's 102 defective scales, that seems to be a lot, for if we've paid for these things. So we don't want a 58% acceptance on something like this. Okay. Questions about that? Okay, very good. All right, why don't you see what you can do with the next one on your own? Okay, so we read the problem, and we want to know what is the probability that a particular flight will be threatened with the failure of both radios. Okay, so probability, both fail. All right, and so this is going to be the probability, of fail and fail, which leads us to the multiplication rule. We ask ourselves, are these events dependent or independent? Independent. They tell us that they operate independently. So probability of failure times the probability of failure. Okay, and the probability of failure is 0.0035. Okay, and we can just square that if we want to, or multiply it by 0.0035, and you got what? One two. 0.00012. Okay, questions about that? How many people? Okay. All right, we're still wrong if you didn't get that answer. Any thoughts on that? Okay. All right, I guess y'all will think about it. But you got it this way, okay? All right, this way. You got to do it just this way. All right, next one. Assume that Google Inc. hires employees on the different business days of the week, Monday through Friday, with equal likelihood. If two different employees are randomly selected, what is the probability that they were both hired on a Monday? All right, so we're interested in probability of what? Of what? Both hired on Monday. So both for Monday. So probability of Monday and Monday. Okay. Keyword and. We're going to use multiplication. Are the events dependent or independent? Independent. Okay. They're randomly selected, then the day on which one was selected has no bearing on the probability of the other was selected. Okay, so probability of Monday times the probability of Monday, or we could have said the probability of Monday squared. What's the probability of being hired on a Monday? 1 out of 5. Okay, since we're just doing the business days. All right, or we could have said 0.2 squared, which is going to be 0.04. Okay. Questions about that? All right, very good. Okay, well, in part B, it says if two different employees are randomly selected, what is the probability that they were both hired on the same day of the week? Okay, this one is a little trickier, but something we should be aware of. So, probability of same day. Okay, couple of ways we could approach this. Can we possibly use our keywords to approach this? And I'll give you a hint. We'll have to use both and or. No? Okay. All right, we could, but and I'll show you how. Okay? It could be Monday. They were both hired on Monday, right? How else could it happen? Or what? Tuesday. When I say or, I'm going to do what? Add. Very good. So probability of Tuesday and Tuesday. And we would do this all the way out till Friday and Friday, right? Adding them up. We already know the probability of Monday and Monday is what? 0.04. We just did that, right? And it would be the same thing for Tuesday and Tuesday, Wednesday and Wednesday. So basically times what? 5, which would give us 0.20. Okay? That's one way we could have approached it. All right? The other way we could have approached it is if we're going to do the same day, then it really doesn't matter what that day is. The only thing that really matters is what? That the second one matches the first, right? So given, it doesn't matter. Pick a day. All right? What's the probability that the second one is going to be Friday? Not 0.04. Well, if you select just Friday, yes, in particular, it would be. Okay, but any day. Doesn't matter what the first day is. Yeah, or we could just say 1/5, right? Because it doesn't matter what the second day is going to be. It would match the first. All right? Pick any day. And so we get 1/5, which is exactly what we just got. Probability of both same day. Both same day. We'll write it this way. Probability that the first is any day, which is basically 1 out of 1, right? Or 5 out of 5, however you want to look at it. Following me? Time the probability that the second matches the first. Okay, and so basically there's only going to be 1 out of 5 that would match the first. So we get 1/5. Okay, which is the same thing as 0.20. We'll come back to that a little later, I think. Okay, but just think about that. The key thing I want you to think about is when we talk about matching things, the first one, it can be anything because he doesn't have anybody to match. All right, and then after that, we got to think, now how do we match it? Okay. All right, and C, what is the probability that 10 people in the same department were all hired on the same day of the week? In such an event, or is such an event unlikely? Okay, so the same kind of principle, probability 10 on same day. What day? Does that matter? No. Okay, so the first one, he can choose any day of the 5. 5 out of 5. But if everybody else is going to match, then it's what? 1 out of 5. Okay, they have to match whatever it is he chose. And how many more people do we have? This is the first, so we've got 9 more people. Okay. 1/5 times 1/5 times 1/5 times 1/5. We have to do that 9 times. Well, the 5 over 5 is just 1. So yes. Okay, questions about that? All right, very good. I put a lot of problems in here because I want you to be prepared for everything. However, I think we'll move on to a different idea. I think I've covered everything in this section. And so try some of these between now and next time. You'll see some videos on these things as well. Okay, but yeah, I just went crazy. Okay. I want to try this one with you, and then you try this other one for later on your own. Okay, it says an automobile manufacturer has 3 factories, A, B, and C. They produce 50%, 30%, and 20% respectively of a specific model of car. 30% of the cars produced in factory A are white, 40% of those in factory B are white, and 25% in factory C are white. If an automobile produced by the company is selected at random, find the probability that it is white. Okay, that's the question. All right, so don't jump to the numbers. Don't even think about the numbers just yet. What I want you to think about is, how can we possibly get a white car from this dealer? And I mean, I'm talking break it down. We got to break it down into our keywords. Okay, so if I'm going to get a white car, where did that white car come from? From the factory. Okay, which factory? A, B, or C. So we could have it, we could get a white car from factory A and white. What else? Or, I heard or, so that means I'm going to do what? Multiply, or that's right, add. So factory B and white, or factory C and white. We have to think this way before we even touch the numbers. No need to rush to the numbers. You got to spend a little bit of time thinking. Okay? But you see how we took this event, whatever it is they're asking us to find, and we broke it down into the keywords, and an or. Okay? So now that I have that, I might write it out. We're talking about the probability of getting a white car. That's what we're interested in. It's going to be the probability that the car came from factory A times what? Well, not just white, but what? The fact, or the probability of it being white depends on what? On what? Something else. Yes, but we want to think about why we're doing that. Why we're doing that. Okay, what is our multiplication rule? Okay, let's take a step back. We've got keyword and. We already said that this meant multiplication. The question we ask is, are these events dependent or independent? They're dependent. White depends on which factory the car came from. Right? Okay? It changes based on what? The factory that it came from. Okay? If we go back to our definition of dependent and independent, we would say if the probability of it being white was the same at each factory, then the factory has no bearing on it being a white car. Following what I'm saying here? Okay. So this is the probability of white given that it came from factory A, plus the probability of factory B times the probability of white given factory B, plus the probability of C times the probability of white given factory C. Okay, now we can put some numbers in here because we know we have a solid rule based on the things that we've talked about. Okay, the probability of it coming from A is what? 50%, so 0.5 Probability of white given A is 30%, 0.3. 30% of the cars are produced in factory, or that are produced in factory A are white. Okay, that's conditional probability. All right, and then I think you got it now. 0.3 times what? 0.4 plus 0.2 times 0.25. And when you do that, you get what? 0.32, or 32%. Okay? So the probability of selecting a white car randomly would be 32%. Okay? Very good. All right.